Yeah, so I'm going to talk about obviously robot manipulation, and we've been interested in that task for a while now. And as many other research groups, we really want to try to go beyond simple, let's say, object pickup or object grasping kind of tasks. And I think one inspirational area for that is, of course, the task and motion planning community. And in this talk, I just want to kind of relate the work that we've been doing to the TAMP setting and how we used it also for inspiration for some of the work that we've been doing. So in task and motion planning, the main focus is really on coming up with planning systems that work at two levels kind of abstraction, where you have kind of a higher level discrete state of the world that you can also describe with logical expressions and preconditions, post-conditions, effects, based on which you can do planning, which is again typically done in a discrete space. And then you combine that with a continuous planning space that is now the space where you actually move, for example, the manipulator in order to pick up certain objects. And the key advantage of these techniques is that they can really approach very complex tasks. They work extremely well in many of these manipulation related settings. But one of the main limitations so far has been that they often work in simulated settings, that they make strong assumptions, for example, about knowledge about objects, knowledge about object shapes and where they are in the environment. And what we wanted to see is how we can make these kind of techniques easier or more robustly applicable in real world robotic settings, and also how we can leverage them actually to train, for example, perception systems for robot manipulation. So in this talk, I'll have three kind of sections that I want to bring up here. And they're all, again, related to this kind of task and motion planning. When the first one is an approach that we started out with when we said that there's all this great work already out there in task and motion planning. So how could we make that possible and robustly execute that in the real world? Even making the same assumptions that many of the TAMP approaches do, which means, for example, that we know objects and that we have models of the environment. And the approach here was to say, well, we'll just train object detection systems and tracking systems to explicitly estimate exactly the kind of states that the task and motion planner cares about. So, for example, when I mean explicit state estimation, I mean, for example, that we're really trying to estimate the 60 poses of objects. By 60, I mean 3D position XYZ and 3D orientation. Again, under the assumption that we have 3D object models, that we are estimating where the robot gripper is, where it is in the environment. And also, for example, if you want to have a robot operating in a larger scale environment, we want to track and estimate the state of all the doors and drawers in the environment. So here the focus is really kind of coming up with a very explicit state estimation based approach. The second line of work was then trying to not focus so much on this explicit state estimation, meaning that, for example, well, maybe we don't even need to ever estimate the 60 pose of an object in order to manipulate it. So this brings up the line of work that I might call implicit state estimation, where we're actually training visual recognition systems with a supervision coming from task and motion planning systems, such that they solidly focus on detecting the kind of logical predicates that a task and motion planning system actually cares about, because it doesn't care about the 60 pose possibly, right? And also training the system such that it can generate the kind of information that is necessary such that the robot can execute its task. So, for example, it could be, again, rather than estimating an object pose, it just asked, is the object currently graspable? Is the drawer open, or is the gripper around the handle of a door or something like that? And then finally, I'll come up with the approach that I call here just like no state estimation, which means we're even trying to get away without doing any of this explicit estimation, but really try to see, can we just go from the raw point cloud data, from the raw perceptual data directly to control tasks, or also to grasp decisions. And that is line of work that we started a bit more than a year ago. Okay, so let me first start with the first part, which is on explicit state estimation. And that is the one that's kind of, I guess, comes most naturally to people who've been working on robotics and state estimation for a while, where the first part is really on 60 object pose estimation. We've done various techniques in that area. I'm not going to go into any details here. So we've done work, for example, that you, who is co-organizing the workshop here, did on post-CNN, where the goal of a deep network is, so trained on specific object instances, it learns from the image data to segment out the object, to estimate the center of the object, and then also to regress to the 3D orientation of these objects. And once we have that information, we can use it, for example, then to pick it up and things like that. Another line of work that I want to mention is this DBIM, which is a technique that uses this idea of iterative matching, which is somewhat related to, you could imagine, like iterative closest point, but in this case, it's actually a deep network that is trained to match rendered 3D object models against images, and it outperformed by a significant margin previous techniques based on this notion of really iteratively matching rendered models into the scene. And that now is also working with depth and color information. And finally, the last piece of work is post-RBPF that was presented last year at RSS, where we explicitly actually estimate a full 60 distribution over the XYZ position and orientation of objects using a raw black polarized particle filter. And that technique has a big advantage that it's extremely robust and also is very well suited for dealing with symmetric objects. So again, I'm not going to go into any details here, but these are kind of the techniques that we developed in order to instantiate the information that these task and motion planning systems typically expect during the execution of a plan, for example. Once we have that, we can now combine that with a technique that my student Tanner Schmidt had developed at University of Washington. It's called DART, where imagine we have this kitchen that you can see in the upper left, and we also have this an IKEA kitchen, and we have a 3D articulated model of that kitchen. Then we can actually use an external depth camera to keep track of all the doors and drawers in the kitchen. You can see this in the lower part. In addition to doors and drawers, you can also see these colored, wait, let me, the laser pointer here, these colored objects. These are objects that are detected with these techniques that I described on the previous slide. And with that kind of information, we can now actually perform task and motion planning in this environment and execute it actually pretty robustly in the real world. So you can see this is the robot actually where it used the model for planning, and then it can also kind of execute it by keeping track of the objects and then using that explicit pose estimation in order to execute the actions. Now, I'll anticipate this, but one of the main limitations is really the reliance on the 60 pose estimation, because as soon as that estimation is not very accurate because of occlusions or things like that, the grasping also itself might actually break down. But otherwise, it works actually pretty well, as you can see here. Okay. We can now, and this was done by Kalen Garrett at internship, he's from Leslie Kelpling's group, and we can really connect this with task and motion planning, where here, for example, the task is there's an object, the spam is in the upper or lower drawer, and the task is to find it and then move it into the other drawer. So these are the kind of settings that task and motion planning systems are extremely well suited for. And again, now with this good state estimation system, we can actually execute them in the real world pretty well. So the robot had first opened the lower drawer, saw that there's no spam box in there, now opened the upper one, gets the spam out, closes it, and then puts it into the lower drawer. Okay, so these TAMP systems are extremely well suited for these longer term tasks, and we can now leverage that in the real world. Final example is work that Chris Paxton did now towards more robust execution, where we constantly keep track of the logical state of the system. So you see that Chris actually closed the drawer, the robot in real time can detect that and then quickly react to these changes, right? And then kind of adapt its execution, more or less. And again, all of this, of course, only works because of the state estimation underneath in the system. So here now the robot finally was able to pick up the spam and then put it in the drawer. Okay, so this is kind of one line of work where we really went down the route and said like, okay, let's see how far we can get with estimation. Again, one of the key limitations is any mistakes in state estimation will also translate in kind of failures in, for example, the execution itself. So now an alternative to that is actually trying to not even go for this, for example, this focus on post estimation, but focus more on what does the task and motion planning system even care about in order to execute these plans. So this is now work that Kay Kase did also as an intern. And so the idea here is, again, we just want to keep track of the logical state that, for example, the task execution actually cares about, and also generate the intermediate goals that are necessary to execute a longer term task. So here's, for example, the input to the system is a sequence of images. Okay, you can see them here on the left, along with the joint states of the robot. Then we have a network that is trained to predict the logical state of that execution system. And for example, the logical state might contain predicates like, is the drawer open? Is the sugar box on the counter, and things like that. These are all actually propositional at this point, so all instance-based. The system is trained on those. And then when the system detects a logical state, that goes into the traditional planner, task and motion planner system that can then decide what should be the next operator or action that the robot should execute. And then another network is trained, and these operators could be things like pull the drawer or approach a certain object. And once this operator is then determined, then the network is trained based on the visual input currently to generate an intermediate position for the gripper that the gripper should reach in order to execute that. So for example, to put the gripper on top of the object or things like that, right? In addition to the gripper position, we also impose an additional loss during training such that the network is forced to predict, for example, the future depth camera image and the future segmentation of the scene, but these are actually not necessary for the actual task execution. The task execution really focuses on this next position that the robot should reach in order to execute that operator. Okay, so let me now give you an example for how this works. So this is now first on the logical state tracking. This is a bit complicated. So what you see here is a long list of these logical predicates that the task planner cares about. On the right, you can see the input image data. So what, let's just see in this case, the robot manipulator H wants to pick up the sugar box, okay, which is the one over here. Let's just pay attention to these three predicates that I highlighted here with the purple boxes. On the left is, in order to pick up the sugar box, we first want to guide the robot gripper to a region above the box from where out it can just go down and grasp it. So this is called in approach object region. And then we have two other predicates that we care about, whether the arm is free, which means is there something in the gripper? And then also whether the gripper is currently around the sugar box, okay? So all of these are now being estimated in real time by the perception system. So as you can see here, as the robot is executing, if you pay attention to the left one, the in approach object region, as the robot gets close, it turned green, which means it switched from false to being true. That automatically triggered then the next action of the robot, which means going down to the sugar box. At this point, the two predicates is free and around object, sugar box, are actually not yet detected by the system. So these are false, positive, and negative. But only like 2-3 camera frames later, if I keep on playing this, now they are detected, which means the is free predicate is detected as false, which means it's not free anymore. And it is detected as green, which is a true positive, that the gripper is now around the object, in which case now the task executor can now trigger the next action, which means close the gripper and pick up the sugar box, as you will see. In this video, actually, Chris did something nasty to the simulator where he actually took the sugar box out of the gripper and put it back onto the counter without the robot noticing. And that will cause quite some confusion on the detector, as you will see. So now it's picking it up. And he actually, again, he put the sugar box back onto the counter manually through the simulator, right? So, the detection system now has to detect that the underlying state is different from what it had expected. And as you'll see, as I will keep on playing this animation, you will see that it correctly detects these erroneous states. And then the planner can replan and appropriately realize that it actually has to go back to the sugar box and grab it again. Okay, so you will see this now. The planner goes back to this initial state and now says, okay, I gotta go through the same sequence again. And all these logical states are then again in real time being detected, and they trigger the next action that the robot has to execute. Okay, you can see this now. And then finally, it actually succeeds in that. So far, I focused on the logical state tracking. The network also, in addition to the logical state tracking, it also, whenever there's an operator that is generated by the planner, it will turn this high-level operator into a goal point for the gripper. Okay, so what you see in this video is on the left-hand side, you see the robot kind of operating here in simulation. And on the right-hand side, what you will see is the network then generating this intermediate goal point that the robot should execute according to the plan. So here it should actually put the sugar and spam into the drawer, okay? So pay attention to the network on the right, and you will see that it always anticipates kind of the next goal point that the robot should go to. Now it jumps to the handle. Once it has the handle, it jumps back, and the robot smoothly then follows those goal points in order to reach them. Okay, so again, what the deep networks are doing here, on the one hand side, they keep track of the logical state of the system. Then the planner generates, based on the logical state, intermediate actions, high-level actions, and the deep network then translates these high-level actions into 60 target points for the gripper that the robot can then execute. Okay, so this is, I think, a nice way for really leveraging the kind of capabilities of this high-level planner, but at the same time training low-level perception and action systems so that they can then operate against this using partial observability, which comes through the color data on the left side. We're currently looking at this and trying to do the sim to real transfer so that this will actually then work in the real world. I think this is something that's a bit in contrast to the pure end-to-end learning, where you would just say, I'm giving the robot a long-term goal and the robot has to figure out everything by itself. In this case, we are giving it strong guidance through the task and motion planning, but otherwise the low-level vision system works with actually a pretty loose kind of supervision. So we're not giving it 60 poses. So now I want to come to the last part, which is this notion of no state estimation, which means we're coming from the other end where we say, okay, we're not trying to do anything as complex as task and motion planning. We're just trying to operate on spaces where we don't even know about object poses or we don't have object models, and see how far we can get towards task and motion planning then, okay? This work led by Arsalan Musavian overall. So where the idea is we train, the first part is on a training to pick up unknown objects. So we're using here, of course, simulation to generate a lot of training data. So here is using NVIDIA's Flex and PhysX system, where imagine you have a 3D model of an object and you can sample many different ways of grasping this object, which means many different relative poses for the gripper. And for each of these, you can then in parallel, of course, feed them into a physics simulator, and then you can evaluate which of these grasps are successful in kind of grasping the object and holding it tightly in the gripper, and which ones are not. From that, you now get a large data set that might contain thousands of objects, all of them annotated with 60 grasp points, that have a high chance of succeeding on these objects. We can now use this data to train a conditional variational autoencoder. This is work that Arthur did for ICCV last year, and I encourage you to go to the website up here where we publish the code, and also the data set is available for this as well. So the input now to this, what we call GraphNet, is following. We get a point cloud from a depth image onto the scene, and the CVAE is trained to sample from that point cloud 60 grasp positions for the gripper. Here just like 3 examples, but it can sample like hundreds or thousands, no problem. The issue with the grasp sampling is that this might still generate graphs that are, first of all, not extremely accurate, or they might even be in collision with the object. So we also then have an additional network, which is in contrast to this generative approach, which is more a discriminator network that is trained to take as input the object point cloud along with the point cloud generated for the gripper that corresponds to these graphs coming from the autoencoder. And then this network is trained to predict the probability that this will be a successful grasp. So for example, if the object and the gripper, if they are in collision, then the network clearly will say that's not going to work out. And for the other grasp, it will then check whether it has a high chance of succeeding. Since this is a deep network, of course, the nice thing is it's differentiable, which means we can actually take that network and differentiate through it, compute the gradients with respect to success, and can actually refine graphs through this deep network, which means the deep network will take graphs and refine them in order to increase the probability of success. Okay, I'll encourage you to go to the website if you want to know more about the details of that. Okay, so this is how this now works. Here's some examples on objects that we put individually on the robot. 2 interesting points here is, first of all, the system is solidly trained in simulation at this point. It has never seen a real object, so it's only using depth camera data. Another interesting point is it has never seen objects with exactly that shape, so it's been trained on different objects. In the most recent instance, actually, we trained a single network on more than 8,000 objects from 262 ShapeNet classes, and it works actually pretty well. Training a network on specific classes has even a slightly higher success rate, but that is, of course, then a more focused network that has to be trained on all these different classes. So I think such a more general network, as you see here, is actually preferable. Okay, so far, we assume that there's a single object in front of the robot. Now, if we want to make this a bit more realistic and say we want to grasp object in clutter, then we need to do 2 things. The first one is we need to segment out different object instances in a scene. And this is work that Chris Chi did, student of mine at UW, had a call paper on this last year, that is trained also in simulation to segment kind of typical tabletop cluttered scenes, as you can see here, based on color and depth data. The results we're getting with this network that he has there were significantly better than those achieved as if you would just retrain mask RCNN. I encourage you to take a look at the paper if you want to get more detail. And now what you can do is the following. We want to take a scene like this one, and let's assume we can segment it with the approach that I just showed you. And let's assume someone says this could be an object detector, or a person could just say, hey, I want the robot to pick up object number 3, target object. So what we can do now is the following. First of all, we take the point cloud of that scene. We can kind of cut out the cropped area around the target object, which is the mustard bottle in this case. We can feed this and train GraphNet to generate possible graphs for that object. These graphs do not consider collisions with other objects. So we now can train an additional network, which we call CollisionNet, that looks at these graphs in the scene and eliminates those that are in collision with other objects. Now you might say, that's certainly not a smart idea because you could just do collision checking, but it turns out that by training a network to do the collision checking, the system becomes much more robust because it can actually predict collisions with occluded parts of the scene for which you do not have point cloud data, and therefore a typical collision checker wouldn't even find these collisions, okay? So once we have this pipeline, we can now go into a scene and say the following. So here's a scene that the robot sees. On the right, you can see the camera image seen from the robot's gripper. And let's assume someone says, we want to pick up the coffee mug. So now the network looks at the coffee mug, generates grasps, and realizes that none of the grasps are collision-free because there's too many objects around it. We can now segment the scene and actually use the collision net to find out which of the objects mostly contributed to the white coffee mug, the target object not being graspable. So in this case, for example, it realized that the sugar box is the one that's mostly in the way. We can now revisit the scene, making the sugar box the target of the grasp system. And now for this, we generate grasp. And of course, in this case, the object is graspable because it's not occluded by other objects. And the robot can actually go and pick up the sugar box, get it out of the way, and then it can reevaluate the scene and say, okay, is it now able to pick up the sugar, the white coffee mug, and then finally grasp it. So this is a kind of a line of work where we're really trying to see, can we go without any explicit, let's say, state estimation, can we start building manipulation capabilities that will go towards what task and motion planning systems actually typically can do, okay? All right. Do you have 2 more minutes, or how are we doing here? You?
It would be great if you can finish in probably 3 minutes.
Okay, perfect. Yeah, that works well. So I just want to highlight also a lot of this work leverages, of course, simulation. At NVIDIA, we're working really hard on making this kind of simulation more and more capable also for robotics applications. So here you can see, for example, this IKEA kitchen system that we have, for which we also built a photorealistic simulator. And so the idea is that really we can build simulation systems so that we can test and also train robots in simulation, not only on the physical aspects of these scenes, but also on the visual aspects, right? Making them photorealistic so that we can train appropriately the object detectors and all these kind of systems. So this is still, all of this is still ongoing work, but there's already first systems out there that are being published as part of the Isaac SDK system, that also these simulators have ROS interfaces, so you will be able to leverage those. I think moving forward, content creation is just a big problem, meaning who builds us these nice environments, right? And there's work on doing this, hopefully through just trained visual system like GANs, generating photorealistic environments, but I think there's still a lot of work to be done in that area. So let me come to the conclusion. So I think, again, in manipulation, we should really look at the bigger pictures and look at longer term tasks that we want to do in manipulation beyond just grasping. I focus today a bit more on how this connects and relates to these task and motion planning systems. On the one hand side, through explicit state estimation, and the other one was implicit state estimation, where we're using the TAMP system more or less to guide visual perception systems to just recognize the pieces that are important for that. And I think the advantage of that approach over just a purely kind of deep RL-based approach is that we can provide much more guidance to the visual training systems and therefore hopefully avoid overfitting to very specific settings and learn kind of recognition systems that are more general. But this is also still very early work in that domain, right? And then finally, I think also promising directions, of course, coming from the perspective where we say, well, let's see how we can start something from the bottom up, where we try to train to manipulate unknown objects, coming much more from a raw data perspective, and then build this up by adding kind of a more and more complex manipulation scenarios. So for example, with the system that I just showed you, with similar approaches, I can well imagine that you can train a system to place objects in a scene, also to grasp objects according to affordances, and also kind of to handle cabinets. So the interesting question will then be, how far do we have to go, or how far can we chip away from these traditional task and motion planning capabilities coming from this bottom-up approach? And with that, I'd like to thank all the great students and interns who worked on that, and also, of course, the NVIDIA researchers and our collaborators. Thank you.